what I would like to talk about now is how to make a measurement in quantum mechanics, which is kind of what we've been talking about up till now. But I want to kind of give you some more of the nomenclature of how this is done. So what we usually talk about is we have some vector basis psi, which we can write down as the sum of all possibilities, omega sub I, projected onto that basis psi. And if we want a particular measurement, so what is omega 2, what's going on there, then we have to project it onto psi, which I've defined as the wave function. That this wave function is this projection of that particular result onto the total vector state. And this right here is called collapsing the wave function. Or collapsing the vector state. But most people say collapsing the wave function. So basically I have all the possibilities in psi, and then I'm curious to see what's going to, is it possible to get the answer omega 2? I look at the projection of omega 2 onto psi, and then I get a result, and this basically gives me the amplitude, which when I square it is going to give me the probability that that's going to occur. So again, if we look at something like position and momentum, these are conjugate variables, or conjugate coordinates, which means they're related. They're related to each other. Mathematically, what we could do is we could write down and say, what is the momentum state P? Well, I can now, since these are continuous variables, integrate over how x projects onto the state P, and then integrate over all space. And so now what I have is I have this projection of position onto momentum, and so now they're related. So the state P and the state X are linked together. And this doesn't happen in classical mechanics. In classical mechanics, usually position and momentum are not related to each other. I could do an experiment where I have a collision. So I have one car colliding into another car. There's an inelastic collision. But I can have that collision either on Main Street, or I can have it in Syracuse, or I can have it in Australia. It can happen in these different positions, but when those two cars collide, then pretty much the same thing is going to occur, whether it happens in Buffalo or Syracuse or Australia. But what quantum mechanics says is that not necessarily true. Is that depending on how I define my position states, that projection of the position onto the momentum could influence and have a slightly different result in Buffalo or Syracuse or Australia. Now, for the most part, we don't really observe those, but mathematically it is possible that we could have a position-dependent type of collision. Now, so that kind of, reinforces what, kind of keep saying over and over again, is that classical mechanics is deterministic, meaning that, I can set up the experiment of, of a collision, and then I can basically determine what's going to happen based on all of the input parameters, and I can do it, pretty much make that calculation and conduct the experiment and see what comes out and get, I can determine the result just based on Newton's laws or conservation of energy or using the Lagrangian, and I can determine basically ahead of time what that result is going to be. Quantum mechanics, on the other hand, is probabilistic. Meaning that I can make a prediction, but this prediction is only telling me what the most likely outcome is going to be. I can't predict whether or not when I can't determine with 100% certainty, I should say, that if I, take one proton and collide with another proton, is that collision going to create a pion? Is it going to create another proton? Is it going to create the Higgs boson? That it depends on the probability of something occurring. And so the probability of creating a Higgs boson, which is a very, very massive particle, is the probability of doing that is low, whereas the probability of creating pions in my proton-proton collision is fairly high, because the pion is a very light particle. It's very easy to convert energy into mass, and so in that case it's much more likely to occur. So therefore, we can calculate the probabilities based on what wave function that we have, and then we can do the experiment to actually see if we get that same probability. So in the end, to do an experiment that wants to test quantum mechanics, it has to be done statistically. So our statistical measurement here is to basically either have let's say one collision conducted n times, or to have n collisions conducted, say, one time. It's statistical. And so, it's kind of like the example of how do you know that the probability of flipping a coin and getting a heads is going to be 50%. Well, I could either take one coin and flip it 100 times, and through those 100 flips, 50 of them should be heads, 50 of them should be tails, and the probability I can state just from that measurement is that there's a 50-50 chance of getting a heads if I flip a coin. Or I could take 100 coins, flip them all at one time, count them up, and 50 of those coins should be heads, 50 of the coins should be tails. So that's how I kind of determine experimentally, or test experimentally, what the amplitudes of this wave function are going to be. So it's not saying that things are particularly random. It's just the fact that that's the only way we can kind of communicate between theory and experiment is the theorist will measure the theorist will calculate what the probability of one reaction occurring is going to be based on all the inputs they know about the wave function, and the experimentalists actually will conduct the experiment, and then they will find out and see whether or not the strengths that they gave to each amplitude in the wave function are correct. And if they're not correct, then the theorist has to go back and try and figure out, what part of my wave function did I need to modify in order to match up with the results that I get from my experiment.